is about ActiveScan++, which is a Python plugin for Burp Suite, and it's also about the new opportunities that are associated with integrating vulnerability scanners into intercepting proxies. So first off, about me, the bio in the program is actually about someone else. So I'm a security consultant at Context Information Security. Spend most of my time web application hacking. And in my own time, I also do a lot of vulnerability bounty hunting. And I found that the most effective, or at least the most enjoyable approach to that, is to look for the issues that other people haven't bothered looking for, that they haven't thought of. And to that end, I've done a fair amount of research into host header attacks. So this talk is going to cover this approach to vulnerability scanning, what the difference is from a classical vulnerability scanner, where you just run the scanner and it crawls the site and then tests everything in an entirely automated way and spits a report out at the end. Then I'll talk about the specific techniques that ActiveScan++ uses to find issues and how the underlying issues work and how to practically exploit them once ActiveScan++ has found them. And finally, I'll talk about some current research into finding vulnerabilities in a more generic way, more oriented towards finding unknown and interesting vulnerabilities. So first off, with a classical scanner, you only really have one goal, and that's finding complete vulnerabilities and reporting them to the end user. With a proxy plugin, you are integrated into the manual testing process, and as such, there's a wealth of information which wouldn't be useful to an end user, but is invaluable halfway through a test. For example, if a scanner finds that it can inject HTML syntax characters, but for some reason can't get any HTML tags in or any script tags or the like, then it can't really do much useful stuff with that, because it can't report it as a vulnerability, because as a scanner it doesn't have the capability to prove that it's a vulnerability. But a manual tester may well find that information very useful, because they could probably bypass whatever's going on that's preventing HTML tags from being injected. And another example of information that's almost innocuous in a final report is version numbers. They aren't very useful at the final stage. I mean, it's worth knowing if something has known vulnerabilities, but if you find out that something is running a version of PHP that has registered globals turned on by default when you're halfway through a test, then that could seriously affect the techniques that you use to test the application. You would start to look at things like guessing parameter names and the like. So there's the software version reporter extension currently in Burp, which does that. It's also fundamentally a lot easier to write a scanner as a proxy plugin because you're standing on the shoulders of the manual tester. All of these issues which typical scanners run into and work around as best they can and put a lot of effort into dealing with are avoided. Everyone who's run a scanner has probably found that they find a contact us form and then submit it several thousand times and take out an email server somewhere. And even if scanners are advanced enough to recognize something like that, I don't think any can negotiate something like a checkout process on a live site that involves adding something to your cart and supplying real credit card details, actually buying an item. They aren't going to be able they aren't going to be able to do that, but the manual tester can, and that they can guide that and avoid all of those problems. As a burp plugin, this tool, there were a couple of issues. Burp is not open source, so it's entirely API bound in what it can do. There are various cases when there were things that I would like to implement that weren't possible because the API was too restrictive. However, Z-attack proxies, proxy plugins, obviously wouldn't have that issue. So those two key differences redefine what information is useful and how easy it is to get that information. And the result is that it's very easy to find serious issues without writing much code for it. For example, that's the majority of the code that I wrote to detect when eval is being called on user input. And it just sends some payloads, times the responses, and sees if they take longer when I tell the server to sleep for longer. And it honestly took longer to write those payloads so that they would work in as many contexts as possible than it did to write the actual code. However, Active Scan++ is really an opportunistic tool looking for issues that aren't detected by Burp's built-in scanning capabilities and that are tedious to find manually, and these tend to be more esoteric attacks, such as those using the HTTP host header. The point of this header is to tell the server which virtual host on that server you want to talk to, like which application on that IP you're communicating with. And historically, this host hasn't been used for attacks very much, it hasn't been tampered with, and people tend to trust it. For example, that's some code that I found on GitHub, and it shows that the developer looks at the host header, sees if it's localhost, and if it is, they think this must mean it's being accessed from the local box. So it must be a development environment, and it's safe to enable debugging features and the like. The reason it's seen as being fairly secure against attack is because the most obvious thing, the reflected cross-site scripting style attack is not really plausible, because we can't make our victim send a malicious host header in a way that's useful. So that just doesn't work. We can trigger a tainted server state, but we need some kind of side channel to get that state to the target. The easiest such way that I found is using site's password reset functionality. If a user says, I want to reset the password of this person, and sends a malicious host header, then the application will take that host header and use it when they generate the password reset link. And the victim will receive a link which, if they press it, will communicate their secret key to the other user, giving the other user control over their account. That issue has affected a wide range of web applications and frameworks, primarily because it's surprisingly difficult to find out where your server is really located. So sites fall back to using the host header. The dotted line on that diagram shows an alternative attack where, if you're lucky, that application will place the host header in an email header, and then you can simply CC yourself on the password reset email. And you can, in that case, you can generally also attach a zip bomb, which the victim's email, webmail provider will recognize and drop the email silently, so they never even receive it. However, that attack generally does rely on the target clicking on a link in an unexpected password reset email. cache poisoning is much more fun. Simply, if they've got a poorly configured web cache, then when you send the request to the server, your response, which has the malicious content in as per like a standard reflected cross-site scripting thing, gets cached by the web cache and served up to everybody else. So with a single request, if it's well timed and well crafted, then an unauthenticated user can gain complete control of the homepage of their target website. This attack is quite tricky in practice. On standalone caches like Varnish and Squid tend to look at the host header when they're when deciding whether to cache a value or not, because they might be in front of multiple applications. It was possible to trick Varnish, however, by sending two host headers, because Varnish would look at one host header and the backend application, if it was Apache, would look at the other host header. The most effective target for this kind of attack that I found is the built-in caching systems in Joomla and Typo3, and I expect in similar systems, because they're part of the application. They don't look at the host header, so they assume that it must be safe, or the request would have never reached the application. So in order to detect this kind of vulnerability, you could write something that combine the many techniques and actually try to find a cache poisoning vulnerability by performing a cache poisoning attack. I tried that last summer. It's extremely difficult and isn't very effective most of the time. However, simply by sending a few selected requests and seeing whether our malicious host header is reflected in the server response tells us whether that application is using the host header, which is a very good indicator of whether it's vulnerable to one of those techniques. So the first such request is perfectly simple. Just send a bad host header. It's important that the referrer always matches the host header, because applications often check to see they match as a cross-site request forgery defense. The second request uses an absolute URL in the request line, and that's necessary when the application that's being targeted isn't the default virtual host. So Apache will see that request line and give that precedence over the host header and route it to the correct application. But the application will often actually look at the host header itself. Finally, in some cases, such as when something is hosted behind Cloudflare, you just can't get a request with a malicious host header to the target. However, the X-forwarded host header is widely supported and used instead by many frameworks. So that comes in very useful. Okay, around a month ago, Typo3, which is a popular content management system mainly used by businesses, I think, reported this vulnerability. And as you can see from the advisory, it's slightly vague. It does sort of imply that password reset poisoning is a plausible attack. So let's have a look at this. Okay. Proxy. Need Firefox. All right, so okay, that's a default typo3 installation with the addition of a username and password prompt. And sorry?
You can do screen mirroring so that you see the same.
Yeah, this should work out okay, I think. Yeah, so if I refresh this, catch the request in burp, and then run and then run an active scan of that, then we should quickly see that there's a host poisoning. That's interesting. Okay, I've no idea what's happened there, but I have a video. So, right, default typo3, and I'll just run an active scan on that. And so that will just send those 3 requests that I showed earlier, and see if any of them get reflected in the response. So we can see here it's found this issue, and it's attached several requests. That's the standard request and response, and that's the attack request. So we can see there that the input that we gave in the host header has been reflected in the response, which implies that this is vulnerable to host header poisoning. So first off, if we take the base request and then change the host header, we can see that we get a different application, which is just a test page because it hasn't been configured. That's because it's not the default virtual host. But if we then specify an absolute URI, then we can put whatever we want in there, and the application will use the host header, but the server will use the request line. So then it's simply a matter of requesting a password reset for someone and using that technique. And then, so we need control of a user account on the system in order to test for this issue properly. But if we didn't have one and had a list of usernames, we could generate a large number of emails like that and see if we got any hits on our site with password reset tokens in. So there we can just see the resulting email with the poisoned link in it. Okay. Now, let's see if we can do a cache poisoning attack. If I do. Okay, great. So, pretending that my scanner already found that issue, we know how to get a request to the server with a bad host header. like this, right? So we can put whatever we want there, and it gets reflected in the response, right? So when testing for cache poisoning, the key thing is to make sure that you aren't getting cached responses, because if you're receiving a cached response, then the issue really isn't visible to you. With most applications, you can do that by doing a force reload in the browser, which adds a header which says "Don't give me a cached response." Typo 3 doesn't respect that header. In order to do this in Typo 3, what you actually need to do is add a parameter called noCache and set it to 1. So if I send this now, then we can see that our input has appeared in more places than it previously was, such as in that base tag. And as is very common with that header, it hasn't actually been HTML encoded, so we can directly inject scripts here. This isn't necessary to perform an attack because it's the base tag, so there are plenty of other things that we could do here, but I'll just use this for simplicity. So this is the response that we want to get cached, and in the case of Typo 3, I've found that the best way of doing this attack is waiting for the cache to expire and then sending our request. In this case, I'm going to trigger the cache expiry so that we don't have to wait. So that should mean that the cache has been cleared. So I can send this response, and that still won't get cached because of this parameter. But if I change that to 0, then it should get cached. So from now on, whatever I put here, hopefully, we can see our injected HTML. And that means if I load the home page as a normal user, located anywhere, because this is cached on the server, then our injected content fires. So we've got full control over that. Okay, shifting back. So no talk about the host header would be complete without mentioning DNS rebinding, a much older vulnerability using this header. This is based on the fact that the same origin policy is all about host names and not IP addresses. So an application can hop between different IPs while remaining on the same origin from the browser's perspective. So in brief, we can serve the user some malicious HTML, tell them to cache it, and then tell them that we are now located on localhost. And our cached HTML and any JavaScript in there will thus have access to localhost. In effect, with this technique, we can proxy through the user's web browser to access internal resources. This attack was partially fixed by browsers by DNS pinning, which just means that browsers won't believe you when you say you've moved like 2 seconds after you said you were in a specific location. However, when browsers are restarted, they do re-request the location, and they've said that they can't fix this for usability reasons. Servers may really move, and therefore they can't fix this anymore. It's the responsibility of the server and the application to fix this issue. And this means that as testers, if this issue is relevant, we should flag it. And in some cases, quite close to home, it's very relevant. Burp Suite Professional has a web interface which is only accessible on localhost, and lets you view all of the traffic that you've proxied through burp, whether SSL or not, and this interface has no authentication on it of any kind. So up until about up until a couple of weeks ago, it was possible to gain access to the full history of any burp user by using this technique. It's now been fixed in the professional version, at least. To address these issues, it really boils down to making the host header as trustworthy as people assume that it will be. And that can be done by using a whitelist of trusted hosts. That's how the major frameworks have dealt with it. They allow wildcards, which can backfire, aside from people whitelisting star, obviously. One major company whitelisted all of their subdomains. And that was a problem because one of their subdomains had persistent cross-site scripting on it, so I could direct users' reset tokens to that subdomain, wait until they ran into the cross-site scripting payload, and then use document.history to grab the token from the browser's history. Also, obviously, the host header is user input. It should be treated as such, and caches should always pay attention to it, and reject requests that have multiple host headers. A naive way to deal with this technique is to use relative links. Relative links can backfire, as Gareth Hayes reported fairly recently. In particular, path relative links rely on the web browser working out where the current page is located on the server, like what the path is. And in some cases, we can trick the web browser about what the current path is, such as on JSP and PHP applications. We can generally put arbitrary content that the browser will think is part of the path that is not, such as there. That semicolon signals the end of the location from the server's perspective, but not from the browser's. So if you load that page with that kind of style sheet include on it, then the browser will end up loading the current page as a style sheet. And this is a problem because style sheet parsing is extremely lax, and style sheets can contain JavaScript and Internet Explorer and do various other bad things in other browsers. So the web browser will load the current page as a style sheet and then walk through it until it encounters any CSS and then execute it. So I've just covered three of these requirements. You need the right kind of server, and you need some kind of input onto the page to put your CSS on that page, and you need the path relative include. The first two of these are really tedious to look for manually, especially because a web application will tend to have a doc type on, say, every page apart from one where they forgot to put it there. So ActiveScan++ passively looks at all of your responses and flags pages that are missing those two, that fulfill those two requirements, and lets the user deal with the rest. I can't demo that issue, unfortunately, because although I found it in some fairly major software, it hasn't been patched yet. So, finally, as developing part of ActiveScan++, I've been looking at how scanners currently work, how I can improve them. That's a classic directory traversal vulnerability. The application can be tricked into interpreting arbitrary files on the local file system as PHP or reading them in and printing them out. And vulnerability scanners look for this vulnerability by using a payload, something like that. That's extremely common. I've seen that exact payload being used in multiple different ways. Nulls don't work. Yeah, exactly. This payload has many, many problems. If null bytes don't terminate, as in modern PHP, then this technique won't work. If the red file isn't displayed back, it won't work. If there's an input length limit, it won't work. If it's Windows, it won't work. And scanners can try to deal with this by adding more and more payloads, but the payoff of each payload drops when they're that specific. And they will always miss things that are vulnerable to this technique. And what I've been looking at is breaking the techniques down to the absolute minimum required to establish that there's something suspicious going on that's worth investigating. For example, if the 573 input gives you a receipt for something you've bought, /573 gives you the same receipt, and /dot breaks the application or gives you a different receipt or a different response in any meaningful way, then we can tell that input is being used in a path, almost for certain, I think, and that it's worth manually testing heavily for that kind of exploit. And just as with manual testing, we can use similar sets of payloads for other vulnerabilities. Any kind of server-side issue where you can inject syntax like that. The keywords there were identifying significantly different responses, because HTTP responses are well known to be extremely variable. They have all kinds of content that just changes every single time. They often reflect input, which is fairly easy to handle, but they will also transform the input in unknown ways by encoding it and such like, which is harder to recognize. They will put timestamps in, and they will just put random input in. And some scanners try to handle this by fingerprinting the document structure. They effectively remove everything that isn't a HTML tag and say, that's what the page looks like. If they start putting new tags in or changing the order of tags, then something major has changed. And it's reasonable, it does the job, but it will miss things. The approach that I've taken is detecting these fuzzy points within the page so that when they change, we can go, I was expecting that to change. I can disregard that. In other words, I'm generating a regular expression to match what a page looks like when it gets a standard input. And by fetching a sample of inputs, we can do this. So this shows the result from a page from a real practice application, and we can see over here where user input has been reflected, and the application has it hasn't recognized that as user input, but it's seen that it's changing and just filtered it out. So whatever appears there, it won't think that that's an interesting result. It's the same with the PHP session ID up in the top. So when this technique works, it gets very interesting results. It isn't public yet because applications still break it. It has serious performance issues associated with generating regular expressions for very long responses. but it has found very interesting issues. Mostly issues that I couldn't exploit personally, but I would love to view the source code that generated those kinds of things. And I think they may have been exploitable given that source code. And it finds issues in such a different way that it finds different things from other scanners, which is very interesting. I'm tempted to say that it's a little bit like an nmap for websites, right? It just pokes at the website and tries to work out where the interesting responses are, like how different inputs are being handled, and should show you which ones are interesting and worth investigating further. The obvious next step would be to tie payloads to specific results. So if we see that that directory traversal case, try a large set of payloads related to that and see if we can refine it and get a better idea about what's going on. Okay. Yeah. So the take home is that proxy plugin scanning unifies manual and automated testing in a really nice way. It just lets you stand on the shoulders of the manual tester. Existing solutions are far from perfect and can be easily improved on, and writing these plugins is almost painless, which may be a mixed blessing in the quality of the plugins that come out. I can't really talk after my demo, but it normally works. Yeah. Okay. Any questions? Yeah?
Very interesting. Thank you for the great talk. I discovered a similar thing, where we replaced a host header, and I did some research on it, and I think a host header, which shouldn't belong to the any virtual host on, for example, Apache, would just give a 400 or something like that.
No. On a
Well, according to the HTTP 1.1 RFC,
yeah.
and in some systems it does, in other systems it doesn't do very well. For example, I saw that you were using a Fedora system.
Yeah. Yeah. I've.
Ubuntu and so related, I didn't see that. And if you cannot manipulate a host header, you get a 400.
Even if you send an absolute URI.
Yeah.
Okay. I have found this in a wide range of externally hosted sites, so it's certainly a pretty common setup. And yeah, what I found is that Apache has a default virtual host, and if it and typically if it gets a host header that it doesn't recognize, it hands that request to the default virtual host.
Okay. Yeah, it could be that's a default setup of different systems.
Yeah.
Or systems different. Okay. Thank you.
Okay. Any other questions? Sure. Thank you.